Okay, so welcome back. And uh, so last time we discussed zero sets of polynomials and we saw some example. So this time, let us come back to, and we ended by saying that all maximal ideals of Cx1, x2, xn looks like x1 minus a1, x2 minus a2, and xn minus an. And for n equal to 1, we have proved that. And in other words, if you take a non-zero ideal, which is not the whole ring, in Cx1, x2, xn, then the zero set of that ideal is a non-empty subset of Fn, where F is an algebraic closed thing, not necessarily C. So now we want to come back to algebraic integers. So, and recall the definition that an element alpha in C is said to be an algebraic algebraic number, if it satisfies, so if there exists a non-constant polynomial f alpha x and qx with coefficient in q, for which alpha is a root, right? So, excuse me. So there exists a non-constant polynomial f alpha x and qx uh, for which alpha is a root. Equivalently, you can say that there exists a polynomial f alpha in zx such that alpha is the root of that polynomial, because you can just clear the denominator, and having a non-constant polynomial in qx is equivalent to having a non-constant polynomial in zx for which it is a root. Okay, so I gave some examples, like I have the root of, excuse me, x squared plus 1 e to the power 2 pi I n. I by n is the root of x to the power n minus 1. Root d is the root of x square minus d. 1 by root d is root of, for example, dx square minus 1 equal to 0. And this polynomial dx square minus 1 belongs to qx, right, or zx, right? So I can either say that it is the root of x square minus 1 by d in qx, or I can say it is dx square minus 1, and then it is in zx. So both the definitions make sense. So we have discussed this. And later we'll see that Q bar, the algebraic closure of Q. So what was algebraic closure? It's a field which is algebraically closed and it is algebraic over Q. So, and it is unique up to isomorphism in certain sense, which we have discussed. So the set of algebraic, so the algebraic closure of Q is the set of algebraic numbers. So if you take an element in Q bar, then obviously it's algebraic over Q. So it is so it's an algebraic number by definition. And on the other hand, the set of all algebraic numbers forms a field, and then it is in fact equal to Q bar. So we'll see that later. The next is, you recall the Gauss lemma. We have proven that fx, so this is again recall, fx is a monic polynomial in zx. And if fx equal to gx term hx for some monic polynomial gx and hx in qx, then in fact fx and gx and hx are in zx. We have proven this. So when we are discussing UFD, so fx in zx is monic, then it is irreducible over zx, and that is, so that is, if you take a monic polynomial in zx, then its irreducibility or reducibility over zx is equivalent to reducible over qx, right? So if it is reducible over qx, then in fact it is reducible over zx, and if it is reducible over qx, then it is also, because monic is reducible over zx. So irreducibility over zx and fx and qx are equivalent for a monic polynomial in zx. That's what this says, Gauss lemma. Okay. And there is a general version for a UFD also, that A is a UFD with field of fraction f, and fx is an ax, and if fx is reducible over the quotient field, field of fraction f or quotient field fx, then it is reducible in ax. And fx in ax is monic and irreducible, then it is reducible over kx. So this is the general version. So mostly we'll focus on this, and in particular we'll sort of focus on this, that fx in zx is monic, then irreducible over zx is equivalent to irreducible over qx. Okay, and there is a corresponding version over UFD also, which we have discussed, but at the moment. So as I said, irreducibility. The particular thing is if it is monic and irreducible, then it is. So again, we'll remember this. Let A be an UFD, and let's say A is a UFD, and its field of fraction is F. Then if Fx in Ax is monic and irreducible, then it is also irreducible over. Then it is irreducible over Kx. Okay, this is the version we might use it. So there is one more criteria of irreducibility which may be useful to us, and then we discuss this now. So this is called this is called so maybe I don't highlight everything. So this is called Eisenstein criteria. It says take P be a prime in Z and let Fx equal to x to the power n plus a1 x to the power n minus 1 plus a1 x plus a naught in zx. And suppose that P divides a n minus 1. So it's a monic polynomial in zx. And a n minus 2, a n minus 2 up to a1 naught, all of them. But P squared doesn't divide is okay. So A divides all the coefficients, but not but it doesn't divide excuse me, doesn't divide a1 a naught, but it does, P squared doesn't divide a naught. Okay, then Fx is irreducible in both Zx and Qx. Okay. So if you have polynomial Fx and assume that it is irreducible over and assume that it is of the form such that all the coefficients, it's a monic polynomial and all the coefficients are divisible by P, but the constant term is not divisible by P squared. Then it is irreducible over Zx and as well as Qx. So we'll give a proof, but you look at examples. So for example, x to the power n minus P belongs to, so you consider belong to Zx, where P is a prime. So for example, you can take x to the power n minus and n belongs to n, any n. Then this criteria is satisfied. So you take the prime P. So let's say x to the power. So let's say x to the power. Let's say I give you x to the power 100 minus 7. Then P divides 7 divides the constant term, and all the terms are zeros. In particular, it is divisible by 7. So by Eisenstein criteria, criteria, it is irreducible. So it refers to this. It is irreducible over, in fact, Qx by Eisenstein criteria and Gauss lemma. Okay. So another example is I leave you as an exercise that you take this x to the power p minus 1. So again, p prime. So again, p prime z. This is called cyclotomic polynomial. So let's say phi px defined to be equal to this. Here I would say use that zx going to zx plus 1 is an isomorphism hint of rings. So you can do a change of variable, x going to x plus 1, and then what happens to this polynomial? Okay, you can try to see that. And yeah, so you try to prove that. So this is a very useful thing. And the root of this is e to the power 2 pi I by p, right? The polynomial, this satisfies this. So this is the reducible polynomial which satisfies this. So this shows that this is an algebraic integer. The use of this exercise is corollary. So from corollary from exercise 2. Is an algebraic integer, and in fact e to the power 2 pi I k by p 2 pi I k by p. K by p is an algebraic integer for 1 less than k less than for any k in n. K in n. Of course, if k is a multiple of p, then you can reduce it to this case. Uh, uh, that k is co-prime to n is an interesting one. So if you do this exercise, you deduce that these are algebraic integers, right? I mean, I mean, algebraic integer which satisfies the irreducible polynomial by px. So, for example, you know that e to the power 2 pi I by 3 satisfies x squared plus x plus 1. So you know, if you attach, if you consider k and equal to q root minus 3, which is q e to the power 2 pi I by 3, then the vector space dimension of k over q is 2, because the irreducible polynomial it satisfies has degree 2. So that it is an algebraic integer is you can see without applying Eisenstein criteria also, but you get, for example, here that the degree is 2, or generally you get degrees e minus 1. Okay, and then there is a more general version of Eisenstein criteria that for any UFD A with a quotient field f, again field of fraction or quotient field f of A, and P is a prime ideal, non-zero prime ideal, and suppose you have a polynomial a n x to the power n plus a n minus 1 x to the power n minus 1 plus a n minus a1 x, so this is a1 x plus a naught in this UFD A, and with so it need not be monic, but a n is doesn't belong to the ideal P, and all other coefficients belong to P. However, a naught doesn't belong to P square. Then fx is irreducible over the quotient field fx, and this polynomial fx is irreducible over fx. So this is the more general version. But so let me give a proof of this this version. So version 1, let me call it. So let's give a proof of this. The proof of proof. And the other version will also not very difficult or different. But for simplicity, I'm only doing this version. So let me do the simple version. Proof of version 1 over Z and monic polynomial. So let monic polynomial over Z. So we have fx equal to x to the power n plus a1 x to the power n minus 1. It's a n minus 1 into x plus a n belongs to zx, and p prime, p divides ai for all I, and p squared doesn't divide n. Okay. Then you look at image of fx, say f bar x in z mod pzx fpx, and we know this is a fpx is a field, fp is a field, so this is a PID, and this is also a UFD, right? So here f bar x looks like x to the power or if I x bar to the power n, right? That's how it looks like. Because everything is divisible by p, so they become 0. On the other hand, let's say if fx is not irreducible, if fx equal to gx into hx, zx, okay, and let's say degree of gx is greater or equal to 1, degree of hx is greater or equal to 1. Okay, so we can assume that because it's monic, so I mean, we can assume both of them have degree greater or equal to 1. And then, so let's say gx equal to x to the power n plus b1, x to the power l plus b1, some problem. Okay, so let's put here. So let's see this works. Yeah. So bl x to the power, so let's say b1 x to the power b minus 1 plus bl minus 1 x plus bl, and similarly hx, let's say x to the power r plus b1 c1 x to the power r minus 1 plus of, I can also say n minus l, n minus l minus 1 and plus c n minus l minus 1 x plus c n minus l, where bi and ci belongs to z. Then what happens is that f bar x equal to g bar x into h bar x, right? And and uh, and this is the UFD, so you have this equation 1 and zx and fpx. In fpx, okay, so in so we have that in fpx, f bar x is this, and fpx is the UFD. So so let me add a page here. Yes. Okay, so okay, and this is a UFD, and so x to the power x bar to the power n equal to uh, g bar x into h bar x. So it must be the same factorization on both sides, right? X bar, it's a product of irreducible, and x bar is an irreducible. So it's both sides it will be. So this factorization is unique. So is a unique factorization. And x bar is irreducible. I mean, we can just denote it by x. It's a prime ideal because it's a maximal ideal, in fact, because fpx mod if you call x is isomorphic to p. So it's a field. So this is a product into irreducible. So both sides it must be the same. So that means constant term. So constant terms. So g bar x also must be some x to the power. Only possibility is some power of x, and so g bar x equal to x to the power some r, and hx is also. Uh, so actually, I should denote it by yeah, maybe x bar is a bit misleading. Maybe it's better to call it because x we are in same side. Prefer to generally the coefficients are changing. So yeah. So So g bar x will be equal to x to the power r, and h bar x will be equal to x to the power. Sorry, this was some r. R is already r and n minus r. That's the only possibility, right? So in fact, it has to be L and L minus L, right? This is the only possibility. The constant term of g bar x equal to 0 and h bar x equal to 0 bar in so this constant term. So p divides the constant term of both gx and hx, right? If I lift it to z, but the constant term of fx equal to dl into cl minus l, dl into cl minus l equal to al. It was an is divisible by p square, and that's a contradiction because p square doesn't divide in, right? So that was the hypothesis. Sorry, wrong notation. What did we use here? Yeah, p square doesn't divide. Correct notation. So p square doesn't divide a naught. Sorry, p square doesn't divide in. Oh, a naught. Okay. So a naught constant term. And this contradiction happened because we assume that if this must not be the case, right? So ultimately we arrive at a contradiction. So that means this implies that fx is irreducible in zx and by Gauss lemma in qx. Okay. So this is one thing we noticed, and so this is the proof of Eisenstein criteria over Z, and a similar proof can work over this is the proof over Z, and a similar proof will work over the UFD, general UFD, and as I said, the applications are like x to the power n minus p is irreducible, and the cyclotomic polynomial is an irreducible polynomial, and things like that. Okay, so we learned some new criteria of irreducibility, two criteria, Gauss lemma and so there are two Gauss lemma. One was in the proof of for irreciprocity, and this is for polynomials. They're different. So Gauss lemma for irreducibility polynomials and Eisenstein criteria for irreducibility of polynomials. Okay, next is let us recall again. Third time maybe we are recalling. Second time we are recalling that an element alpha is an algebraic number if there is a non-constant polynomial fx in zx such that f of alpha is equal to 0, right? Now an element alpha is said to be an alpha in C is said to, this was algebraic number, algebraic integer. So it's called algebraic integer, complex number, if there exists a non-constant monic polynomial alpha, monic polynomial fx zx plus that f of alpha equal to 0. So the difference here is again, this is monic. Okay. So, so examples are, so let's give some examples. So examples are integers. So they satisfy x minus n equal to 0. Root d, they satisfy x square minus d equal to 0. Then 1 by 2 is not an algebraic integer. 1 by root d not algebraic integers. So integers Okay, so uh, yeah, so then let's give further example. Uh, so not all are of the form. So let's say root 5 plus 1 by 2. Let's say alpha equals. Let's see what happens with this. This implies 2 alpha minus 1 equal to root 5, or this implies 4 alpha square plus 4 alpha, sorry, minus 4 alpha minus 4 equal to 0, or this implies alpha square minus alpha minus 1 equal to 0. Okay. Uh, uh, so 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 this satisfies. So this is an algebraic integer. So root 5 plus 1 by 2 is an algebraic integer. We have just proved that e to the power 2 pi I by k, and similarly p, and similarly n is an algebraic integer. Algebraic integer is by x to the power n minus 1 equal to 0. And so by Gauss lemma, so this is the definition and some example of algebraic integer, some example of not algebraic integer. So why these are not algebraic integer? So this satisfies, I did not give a reason, but you should be able to prove that they do not satisfy monic irreducible polynomials, monic polynomial over Zx. So I just, in the definition, like in the case of algebraic number, I did not define anything and said about irreducibility. But by Gauss lemma, let fx belongs to Zx. This is the polynomial, is the polynomial of least degree in Zx. I've already said in Zx. Be the, so okay, be the, okay, so we have to make some changes. Monic polynomial of least degree such that f of uh, alpha equal to 0 uh, satisfied by an algebraic integer, then fx is irreducible over zx and qx. Right? Just think about it. Okay. Uh, uh, so if it satisfies the monic polynomial of least degree, then it is irreducible over zx and qx. So so from there you will be able to prove using this. So just think about it, why it follows from Gauss lemma, and using this you'll be able to prove that what I said here, that 1 by half, 1 by root t are not algebraic integer, and you'll be also able to prove that corollary only algebraic, or if alpha belongs to Q and alpha is an algebraic integer, then alpha belongs to Z. Okay. Okay, so I mean, if and only. Then alpha is an algebraic integer if and only if alpha is in Z. Okay. So yeah, this is not hard to show, and Yeah, using what I said. And now you recall, so what we are interested in this course, what happens in the quadratic case. So recall q root d equal to a plus b root d, where a, b are in q. And so let's take, okay, so let's take, um, so let's take d square free integer, and let's say d not equal to 1 to avoid any confusion. And then you take q root d. So this is the a plus b root d, where a, b are in q, and this is isomorphic to qx mod s square minus d. And this is so this is a and this is also um, uh, so so this is a quadratic field, and it's a two-dimensional q vector space over, so two-dimensional q vector space, and with basis 1 comma root d, and this is can be identified with the quotient of the polynomial in qx mod x square minus d. So now we are interested in so as I said, and every element of q root d here is an algebraic integer. So if you write alpha equal to a plus b root d, then this implies alpha minus a whole square equal to b squared d, which implies f alpha equal to 0 with where where x equal to x square minus 2ax plus a square minus b squared d, and this is a polynomial in qx. Okay, so two-dimensional q vector space with basis 1 root d, and every element there is an algebraic number because where a and b are in q, and so every element of q root d is an, so as I just shown, that every element of q root d is an algebraic integer. So now we are considering, now you consider the set of algebraic numbers inside q root d, right? So for example, we just said that you see here, what are the algebraic integers inside q? Precisely z, right? So now we are asking what are the algebraic integers inside q root d. So what is algebraic integer again? It has to be what is the difference, as I said. It's highlighting again. It is algebraic integer if it is the root of a monic polynomial with coefficient in z. Okay? So the main thing is monic polynomial, and we saw some examples. So now we are asking the main theme in this course. One of the main thing we are pursuing in this course, that consider the set of algebraic integers inside q root d. Okay, the set of algebraic integers inside q root d. So this is denoted by OD, and so alpha in q root d, so that alpha is an algebraic. So what will happen then? Then alpha you write equal to a plus b root d, where a comma b in q, and then again you get that. So then, because it is inside q root d, you can write like this. And we are keeping the same premises, sorry, that d is square free integer. And then, so this implies again, you satisfy alpha satisfies x square minus 2ax plus a square minus b square d equal to 0, right? So if alpha is an so it satisfies this polynomial over Q, and if alpha satisfies a polynomial of over Z, then if you choose the one with the least degree, it will be reducible over QX. So alpha, let's say, doesn't belong to Q. So uh, 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 then it generally this is the least degree polynomial to satisfy over Q, and since it is an by Gauss lemma, this has to be the polynomial of least degree, which is satisfies over Z for alpha. So that will imply that 2 minus 2a belongs to Z. So for alpha, if alpha is an algebraic integer, so this will imply that minus 2a belongs to Z, and a square minus b square d belongs to Z. Okay. So both the things are there. So for example, if a comma b belongs to Z, both of them are in Z, then we can see that this condition will be satisfied. So that will imply alpha is an algebraic integer. So again, the reason this is true because alpha satisfies degree 2 equation over Q. So since alpha is an algebraic integer, it will the least degree polynomial it will satisfy over Z will be reducible over QX, and hence that has to. So let's say this is an irreducible polynomial over Qx, and if it is an algebraic integer, that it's a monic polynomial, so that has to divide this in Qx, the polynomial over Z, monic polynomial over Z, it satisfies, and hence it has to be equal to this. Okay, so so you can deduce by Gauss lemma that this is the thing. Then minus 2a will belong to Z, and a square minus b square d will also be belongs to Z. So for example, we can see that OD contains Z root D. What is Z root D? So, Z root D, if I define it, this is defined to be A plus B root D, A, B in Z. But we saw it could be more than this. So for example, you take D equal to 5, then it also contains 1 plus root 5 by 2, just now we saw. Okay, so if you work this out, so you call this, so if AB belongs to this condition is satisfied, but some more cases can happen. We have seen D equal to 5, 1 plus root 5 by 2 is an algebraic integer, right? So more generally, what is the thing? So the answer is exercise. So exercise is that Z root D so OD equal to Z root D equal to A plus B root D, A comma B belongs to Z, and it is Z into 1 plus root D by 2, which is defined to be A plus B into 1 plus root D by 2, that AB belongs to Z, this set. And so this is, okay, when is this? So I have to specify. Okay, so this is equal to, and this set, excuse me, this is also equal to if D is congruent to 2 or 3 mod 4, and this is if D is congruent to 1 mod 4. Okay. So if D is congruent to 2 or 3 mod 4, this will be the case. You can work it out. Also, every element of this form you can check is an algebraic integer. So this is the entire set of algebraic integers. By the way, this set can also be written as A plus B uh, root D by 2 such that A, B belongs to Z and A is congruent to B mod 2. Okay, so one can also describe this set as follows. Okay, so uh, this is the description of uh, this is the description of uh, set of algebraic integers OD. So this is the in particular you can check that in particular what you notice is that in particular OD is a ring that is the set of algebraic integers inside Q root D forms a ring. Okay, so yeah, uh, uh, so so uh, so this is the set of algebraic integers inside this. This is not, if you think about it, it's not completely obvious. If you have two algebraic integer, why their sum will be an algebraic integer? Why their product will be an algebraic integer? Why their subtraction will be an algebraic integer? So every time you have to find a monic polynomial. So if alpha satisfies a monic polynomial with integer coefficient, if beta satisfies a monic polynomial with integer coefficient, it's not clear why alpha plus beta and alpha times beta will satisfy a monic polynomial with integer coefficient. So this is not obvious, and also if we put so also put so you put, we'll discuss these things later, but you put what you do, you put also also put omega equal to root D if D is congruent to 1 mod 4 sorry which D is congruent to 2 or 3 mod 4, and it is equal to 1 plus d by 2, and if d is congruent to 1 mod 4, then OD is z plus z omega, and this is a direct sum, you can see. So is a free abelian group of, or then we can write it this way, then the abelian group of the ring OD, the isomorphic to Z direct sum, the isomorphic to Z square. Yes. Okay. So Z square here means the direct sum Z. Okay. Maybe I should just write Z direct sum Z. And so the set of algebraic integers inside Q root D forms a ring, and this ring has a, so how, and this is not easy to prove, but in this case we can explicitly compute and the set of algebraic integer, and they turn out to be a plus b root d if d is 2 is 3 mod 4, and as I said, it can be checked by this criteria. And if D is congruent to 1 mod 4, then it is A plus B into 1 plus root D by 2. So and such things you can check that this forms a ring. So if you take two elements here, their sum will be here, their subtraction will be here, their product will be here, one belongs here. So this is the ring, and the set of algebraic integer here forms a ring, and if you look at the abelian group of this ring, then this is two copies of Z. Okay, Z plus Z omega. So, what we are interested in this course, what are the ideals in this ring, and what are the ideals in this ring? What are the prime ideals in this ring? What are the maximal ideals at this ring? Is this ring is a PID? And what are the units in this ring? This is what we are going to study in the next few weeks. And when this ring is a PID or not is another central question that we will study. So we'll continue on this. Thank you.